So we are going back and looking at some stuff that you probably did in year 9, but you weren't taking it very seriously then because you didn't really think it was GCSE, but it is, and it counts and it's important. So we're going back over some physics, speed, velocity, and acceleration. You'd probably do these over a few lessons, but I'm squeezing them into one because it's review. And by the end, you should hopefully be able to calculate the acceleration of an object. You should be able to explain the difference between speed and velocity, and you should be able to understand and calculate relative velocity. But to start yourself off, I just want you to name 4 things that you can measure distance with. Name 4 things that you can measure time with, and then put the following in order from smallest to largest: milli, mega, kilo, nano, giga, and micro. Pause the video, answer the questions, and unpause when you're done. Ready? So, let's see, the pen works. 4 things you can measure distance with. You can measure it with a meter ruler. Nice, it works. You can measure it with a tape measure. You can measure it with a normal ruler, I suppose. And you can do one of those trundle wheels that they do in geography or biology when you go outside. Nice. Or PE. Other things. 4 things you can measure time with. You can measure it with a clock. You can measure it with a timer, like a stopwatch. Measure it with the sun. You could do a sand timer, sand dial. That's 4. Put these into smallest to largest. The smallest is nano, then it's micro, milli, then we go to kilo, mega, and then giga. Excellent. I'm sure you got all those right, and if you didn't, learn. Jump straight away into the equation for speed. Speed is the distance traveled divided by the time taken. If you go 40 miles and it takes you 1 hour, you're going 40 miles an hour. If you're going 40 miles and it takes you 2 hours, you're going 20 miles an hour. It's a very simple equation. Speed is distance divided by time. Now, I said miles an hour, but actually when we're doing it in physics, normally we do it in meters for the distance, seconds for the time, which gives us a speed of meters per second for the answer. Just as a kind of rough back of the envelope type thing, if you take the speed in meters per second and you times it by 2, it gives you roughly what it would be in miles an hour. So, for example, if you work, sometimes it's useful, like if you work out how fast the car is going, it's like 15 meters per second. You're like, I don't know what that means. 15 meters per second, is that fast? Is that slow? If you double it, that's 30 miles an hour, which is a kind of normal speed for a car to be traveling on a road that's not in a built-up area. So, meters per second times by 2 gives you miles an hour, roughly. You'll have to, there's more precise calculation for another lesson. Let's have a go. A train takes 100 seconds to travel 1,500 meters. What is the speed of the train? What do we have? We have time here, and we have a distance. So speed is distance divided by time. So 1,500 divided by 100 seconds. Even I, with my maths, can do that. Is 15 meters per second. Is that fast? Is that slow? As I just said, if you multiply that by 2, that gives you 30. So 15 meters per second is about 30 miles an hour. I think it's a bit more. I think it's about 32. I can't remember. And you know the formula triangle. If you put these into the triangle, it makes everything much easier. So to work out speed, you just cover over the S, and we've got D over T, distance over time. But if you don't want that, if you actually want to work out time, we've got distance over speed. Scroll that out, that doesn't help. Distance over speed. Or if I want distance, it's speed times time. The formula triangle, so simple. If you know how to put something into a formula triangle, you're laughing. Another example. A car travels at 25 meters a second for 3 minutes. How far does it travel? It's asking a distance, so we've got to do speed times time. But what do you notice? It gives us a speed in meters per second. but it gives us a time in minutes. So you have to convert. How many seconds are there in a minute? Yes, there are 60. So 3 minutes, 3 times 60. Excuse me. The distance is speed times time. So 25 meters per second times 180, which is 3 times 60, gives us 4,500 meters. A chance for you to do your own questions. Basically, simple. A car travels between two cities that are 100 kilometers apart. The journey takes 2 hours. What is the average speed of the car? A girl runs at a steady speed of 6 meters per second for 12 seconds. How far does she go in the 12 seconds? A bird flies 200 meters in 10 seconds. What is the average speed of the bird? A snail crawling at 5 millimeters per second travels 2 meters along a wall. How long does this take? And a rocket powered by a solid fuel motor only has enough fuel for 25 seconds flight. If the average speed of the rocket during such flight is 200 meters per second, what is the maximum range of the rocket? So, pause the video, answer the questions. Go. Done? Spiffing. The other thing I wanted to note here, in question 1 and question 3, it says a car travels between two cities at 100 kilometers apart. The journey takes 2 hours. What's the average speed of the car? So when you do that calculation, the distance divided by the time, you end up doing 50 kilometers an hour. But the car wasn't traveling 50 kilometers an hour the whole time. That would be very unusual, because normally when you're driving, there's traffic lights, and then you might hit a motorway, or they'll be into a town. So actually, there'll be times when the car was going much, much faster, and times when the car was not moving at all. So the average speed of the car is the total distance and the total time. So there are instantaneous things that are slightly different. And this is an important part. So the difference between a vector and a scalar. So what is the difference between distance and displacement? That says displacement, my head's in the way. So here we have a nice good representation. If you're going from A to B, now you go from A to B in a straight line, like this, or you might not be able to go in a straight line. There might be a building in the way, there's a river or something, sometimes the journey you take isn't necessarily the straight line. And so by the time you've walked and gone around the corner and up the street, you've traveled a distance that is longer than the displacement between A and B. A and B, the shortest distance between A and B, is classed as the displacement. How far you travel, that's your distance. So A to B's displacement, whereas A, C, D, B is the distance. And one of these is a vector and one of these is a scalar. So A to B displacement is a vector, its size and direction. So we're going 34 kilometers north, whereas A, C, D, B journey, obviously it's a much longer journey. You're going 60 kilometers, but it doesn't tell us which direction. We change direction all the time. So if we're talking about something with direction, it becomes what was known as a vector. Vectors have direction: 70 meters north, 200 meters down, 5 miles an hour west. That's a vector. If it's just 5 miles an hour with no particular direction, then it's just a scalar. Scalar, just a number. Vector, a number, but with a direction. Nice. And so the difference between, one of the things in the objective is the difference between speed and velocity. And it's basically distance and displacement. Velocity is a vector and it has direction, whereas speed is a scalar and it doesn't have direction. So the average speed of a journey is the distance divided by the time. The average velocity is the displacement divided by the time. And so if we go back to that diagram there and we apply that, the time for the journey would be the same. Obviously, If you're timing yourself to go from A to B, and obviously the journey you take is A, C, D, B, your average speed is going to be whatever your average speed is. But if you work out your average velocity, the distance you have traveled in reality, the displacement, you've traveled in reality is much less. And so the displacement on the top will be smaller than the distance on the top of the other equation. So where's the pointer gone? So this distance will be a bigger number than this displacement. So this time will be the same. So your average speed will be higher than your average velocity. Like our velocity will be 12 meters per second that way, or that way, or that way, or something. Velocity, they'll both be like meters per second or miles per hour. One has direction, the other one doesn't. Here's an example. Here's some things for you to try. I'll do the first one for you. So in the grid below, each square represents 1 Newton of force. Force is another example of a vector. State the size and the direction of each force arrow. So, well, this one is like 1, 2, 3, 4. 4, but it's not a vector yet because I haven't said the direction. The direction is, where's my pen? So 1, 2, 3, 4, and we've got our compass. Never be shredded. We east. 4 newtons to the east. Can you work out what B and C are? Do it. Write it down. Excellent. So another chance for you to work out what vector and scalar is, or something for you to practice. So I'd like you to put on the top of your piece of paper scalar and then vector. So every time you come across something in here that is either a vector or scalar, write it in the correct column. So for example, I'll do one for you. Ahmed takes 40 minutes to get ready. 40 minutes. Time. No direction. 40 minutes north. Doesn't make sense. Minutes. 40 minutes. That's a scalar. So I'd write 40 minutes. I'll write that in the scalar column. Ahmed takes 40 minutes to get ready in the morning. He usually eats around 50 grams of cereal. How would he know? Does he measure it? Strange man. With 200 milliliters of milk. Very strange. But 2 measurements there. Are they vectors? Are they scalars? After breakfast, he walks 10 meters from the kitchen to the bathroom, where he brushes his teeth with 2 cubic centimeters of toothpaste. To get to school, he has to walk 2 kilometers in total. On the way, he stops off at his friend's house, which is 800 meters to the east of his house. After picking up his friend, they walk another 1,830 meters north to get to school. The doors out of the school are heavy, and Ahmed has to push against them with a force of at least 100 newtons. After school, Ahmed goes for a 5-kilometer jog around the park, which takes him 40 minutes. He aims to burn at least 500 calories a day through exercise. After going for a jog, it takes him around 15 minutes to walk back to his house, which is 500 meters southeast of the park. Well, Ahmed sounds like a hoot, but make sure you've written all the things that are vectors and the scalars in the correct column. Okay. Acceleration of an object is a measure of how quickly its velocity changes. So here we have a very old, heavy train. If you've ever seen one of these trains, or just any train starting off, it's a very slow process. The wheels spin and it barely moves and it chugs and chugs. And then if you leave it for a while, a few minutes, the train can absolutely go really fast, hundreds of miles an hour, or 100 miles an hour. But it takes an incredibly long time to get there. That means it has a low acceleration. Acceleration is how fast can it go fast? How quickly it gets its speed up. So a train will have a low acceleration. A motorcycle, on the other hand, particularly a sporty one, will have an incredibly high acceleration. The lights change, twisted throttle, he's off like a rocket or like a motorbike. Actually, this one says about deceleration of brakes, but they've got to have good brakes too. So how fast you go fast, or how slow you go fast is all about your acceleration. If you can pick up speed quickly, and you go from 1, 2, 3, 4, 5, 6, or do you go 1, 10, 20, 30? And, does it zoom up, or does it get there in the end? It's tricky. How do you calculate acceleration? Well, because it's about speed changing, you need to put the change in speed in there. So acceleration is equal to the change in speed over how long it took that speed to change. It might be easier if we do an equation with a practice, but write that one down, please. Acceleration equals change in speed divided by time taken. Oh, forgot to say, acceleration is measured in meters per second, or meters per second squared, because speed is in meters per second, that's on the top, and time taken is in seconds. So you've got meters per second divided by seconds, which makes meters per second. So here we go. Oh, this is a very old picture. And a racing car accelerates from rest. What's the speed at rest? 0. From rest to a speed of 60 meters per second in a time of 4 seconds. Remember, when you double the speed in meters per second, it gives you miles an hour. So it goes from 0 to about 120 miles an hour in 4 seconds. That's a pretty big change, yeah? 0 to 120 miles an hour in about 4 seconds. That should be big. What's the acceleration? So we do the equation. Acceleration is change in speed divided by time taken. So 0 minus 60, 60 minus 0, you start at 0, end at 60, so 60 divided by 4 gives us 15 meters per second, and that's pretty fast. That driver, probably Michael Schumacher in the olden days, will be going very fast, push back on the car. And again, you can put this into the formula triangle, although that only really works if the change in velocity doesn't work all the time. But basically, A is acceleration, S is the change in velocity, and T is the time, although I might give some different letters later. Here's another question, example. A cheetah accelerates at 10 meters per second from rest until it reaches 20 meters per second. How long did this take? So it's going from 0 to 10 meters per second. No, from 0 to 20 meters per second. Its acceleration is 10 meters per second. How long did this take? Change in speed over time taken gives you, time taken is change in speed over acceleration, 20 over 10. It takes 2 seconds for the cheetah to reach up to 40 miles an hour. Not bad for a cat. I think my cat could probably do that. It's just gone. Okay, so maybe talk about speed and acceleration and things that are more relevant to you. So here we have at the top, Bill Cooper dude. He has a very high speed, which means he can go very fast. He's got medium acceleration, which means it takes him an okay time to get there. So he can go quite fast and he can get there at quite a reasonable pace. But we look at Bowser here at the bottom, this guy here. He's got a much higher speed, but his acceleration is so low. He takes so long to get fast. So at the start of the race, everyone's going to nip off and he'll take a long time. But after a short period of time, he'll be going faster than everyone else. Hopefully no one else has gone too fast. And if we look at Yoshi, well, got a decent speed and a decent acceleration, a good all-rounder. Gets to a top decent speed, but gets there pretty fast. There we go. Copy Mario Kart. So don't finish this first. And now we're at questions. So, you have to answer these questions, write them in your book, and don't forget to take a photo and send it to your teacher. Which of the 2 following measurements are needed for calculating acceleration? Circle the correct answers. Don't circle, because this is on your computer or your phone or your tablet. Just write down the correct answers. Distance travelled, time taken, change in speed, weight of moving object. Which 2? Describe the difference between acceleration and velocity. A ball is dropped from a window. It accelerates uniformly, which means nice and smoothly, at 10 meters per second squared for 3 seconds. An acceleration of 10 meters per second means the ball gains 10 meters per second per second. How fast is the ball going when it's been falling for 1 second? And how fast is the ball going when it's been falling for 3 seconds? Write down the answers. Now, pause the video, write them. Once you've done it, unpause. Okay. Okay. Done? Ding dong. In your answers to the following calculations, write the unit and the suitable number of significant figures. Note, your calculator will just say lots of stuff. Be smart. What is the correct amount of significant figures you should write? In one of the students' measurements, the acceleration was 1.37 meters per second. The final velocity was 1.66. Calculate the time taken. When the acceleration was 2.22 meters per second, the time taken for the trolley to travel down the runway was this. Calculate the final velocity of the trolley. For both of these questions, you must assume the thing started from rest. So the starting velocity was 0. It gets to its final velocity. You can use that to calculate. And you've done. Just answer the questions. Don't forget to send your work in. Love you. Bye.